All right, then let's get started. So it's my great pleasure to introduce Professor Madeleine Udell. Madeleine is a truly outstanding junior faculty in Cornell's RIE department. She works on a broad range of really interesting questions in optimization and machine learning across the spectrum of both theoretical and applied work, including some really cool applications coming from a broad range of disciplines, including marketing, demographic modeling, medical informatics, engineering system design, and automated machine learning. She's been honored with many accolades, including an NSF Career Award, ONR Young Investigator Award, and an Informs Optimization Society Best Student Paper Award. And she's just really outstanding, and I think can play a great role in the system space. Today she's going to be speaking to us about imputing missing data with the Gaussian Copula. And with that, I'm going to mute myself, and please take it away, Madeleine. Thank you.
Great. Okay, so this is joint work, I should say, this is joint work with my PhD student, Yishuan Zhou, who's from the statistics department, and also one former undergraduate, Eric Landgrebe, and Elliot Scheckman, who's a current undergraduate here. So, you know, all of the good ideas are theirs. Okay. Okay, so here's the origin of this problem. It's a problem I've been thinking about for a long time, and I first encountered this problem actually working on the 2012 Obama campaign. So if you think back in time, at that time the opponent was Romney. Okay, so the stakes were high. But here was the problem that we had. So political campaigns, how do they operate? How do they decide what people to reach out to encourage to vote, to encourage to register to vote, things like this? Well, the main data that you start with is a voter file. So this is collected by each state. And so each state has information about each registered voter. And that might look like this. So here I'm showing a bunch of different rows. There's one row for every voter, so I'm showing 4, but there could be as many as there are registered voters in the United States. And I'm showing a bunch of columns that are things that I know about these people. Okay, so here, age, maybe there was a binary field for gender, and there's you can see there's some missing values, right? So age, someone didn't maybe feel like putting down their age. Gender, either they missed that question, or maybe they don't agree with the binary encoding, right? So they don't actually think that right, there's not actually a valid imputation there. What state they're from, maybe their level of education, maybe approximately. And it's worth remarking, so here I'm showing 5 columns, but there could be tens of thousands of columns. It's very easy to buy commercial data, match it with data in the voter file, so that you extend this to extremely large data sets, right? So I'm showing 4 rows and 5 columns, but you could easily have hundreds of millions of rows, tens of thousands of columns. Okay. So when I was working at the 2012 Obama campaign, one of the first questions that I was asked was, can you figure out who these people are? Can you cluster them? Can you sort of find, typical responses within the clusters? Can you impute the missing values, right? And all of these things are made very difficult by the fact that the data has a lot of different types, okay, and has missing values. Okay, so here you can see age is, a real positive number. You'd be surprised if you saw 17.4, for example. Income, also usually a positive number, but the scale is quite different. State takes on one of 50 values. Here, gender has only 2 values in that column, and education, it's an ordinal variable, right? So high school education is less than a college education, is less than a master's degree, but there's no notion of by how much, right? Okay, so it's not totally clear how to cluster data like this, and it's not totally clear even how to impute these missing values. Somehow you feel like you should take account of the distribution of these values. Certainly you should take account of the data type, but it's not easy to do. And any subsequent analysis is going to be affected by how you fill in those missing values. Okay, so our goals might be things like imputing missing entries, estimating the confidence of our imputations. How much, are you very confident about this imputation, or actually are you just widely guessing? To quantify the impact of these imputations on downstream analysis, this is a pretty common workflow. Is first you impute values and then you do some analysis, and you might want to understand like how much have you lost information or possibly corrupted information by doing those imputations. And could you identify which features are similar to each other? Maybe you're buying a bunch of data from a vendor that's redundant with data you already have. You might want to know that. So more generally, here's the setting that we're going to be working in. We're going to suppose that we've got a data table, n rows and p columns. So each one is in statistics, so we're using statistics notation here. Okay, so p features, n examples, and this could be much more general, right? It could be patients in a hospital, respondents on a survey, assets in a financial model. And the features could be, you know, tests that they've taken, questions they've answered, performance indicators for financial data. Okay, so x upper I is going to be the ith row. That's the feature vector for the ith example, right? And that has data of many different types. And the x sub j, that's the jth column. It'll be the values of the jth feature across all the examples. Okay, so a pretty typical approach to this, and the approach that I would have, you know, I would have recommended to you up until this last year, is low rank matrix completion. Okay, so it has a lot of things to recommend it. There, so in that approach, what you do is you model the data by saying there's some underlying latent low rank parameter matrix, and the data is generated by some statistical model that takes this low rank parameter matrix and produces the values. Okay, maybe in some noisy process. Okay, so the nice thing about this is they're efficient algorithms. They admit theoretical guarantees. They work well when the true rank of this parameter matrix is small compared to the dimensions, or when the true matrix is approximately low rank. But on the other hand, they work really poorly for ordinal data or for mixed data, data of mixed types, real valued, ordinal, and Boolean. They also work poorly when even the real value data has some weird distribution, you know, even with something like income, right? You know, it's very heavy-tailed. And if you use something like a quadratic loss function or even an L1 loss function, that can really throw you off, right? These small number of very large values might really, you know, pull your fit away from where it should be. Okay. So all of these, essentially, one way of stating the problem is they require additional parameters. Because you have to write down some loss function that tells you how to connect this low rank matrix with the kind of values that you're observing in your actual data, right? In the data that you collected. Okay, to fit those you know, extra parameters, usually the way you do this is with cross-validation. But cross-validation is very, very slow, right? You need to, you know, for each, you know, in order to validate each choice, maybe you're doing 5-fold cross-validation, so that's 5 model fits for each possible value of these many parameters. Okay, each of the loss functions and maybe also the model, the rank of this matrix. Okay, so you know, even if you say, look, this you know, this low rank matrix completion is so fast to fit, that's not the end of the story because you've got extra parameters that you need to choose. Okay, and that can be very slow. It can slow you down by a factor of 100 easily. Okay. So it's worth stepping back for a moment and asking why. Like, why do these things look approximately low rank anyway? And when should we expect them to look low rank and when not? So one sort of nice sort of, oh gosh, this does not have the references in it. I am going to recompile if you don't mind. Very sorry about that. That's why. Great. Okay, so for large data matrices that are kind of squarish, so that means the number of rows is similar to the number of columns. So in that case, you can show that they're often approximately low rank, So you can see this empirically, and with Alex Townsend, we have a recent result showing that the approximate rank of such a matrix under very general conditions, so some probabilistic model for generating the matrix entries, but essentially the only assumption is some kind of analyticity. The approximate rank grows as the log of the number of rows and the number of plus the number of columns. Okay, so since right, the matrices are going much faster than the log of their dimension, this means that they look approximately low rank when they get big enough. Okay. On the other hand, when you think about a skinny data matrix, even in the setting that we were describing, right, if you've got hundreds of millions of rows, even once you have tens of thousands, maybe tens of thousands of columns, certainly if you have fewer columns than that, notice that there's the naive bound on the rank is just the minimum of the two side lengths. Right? So if the log of the number of rows plus number of columns grows faster than the number of columns, then their matrix is not going to look low rank. So, and often this is true, right? You can have a data set where you just have 10 columns you're interested in, 20 columns you're interested in. That matrix is not going to look low rank, and it's kind of foolish to fit it with a low rank model because you've got lots more information. You have a lot of observations in each column, and you can estimate a much more complex model per column. Okay, so you should do it. Okay. So it's worth noting also that the imputation challenge depends on the data. Okay, so you might think about whether the matrix is skinny, right? Small number of columns, P, versus wide, large number of columns, P. What type of data do you have? Is it continuous, ordinal, binary, categorical, mixed? If it's continuous, what kind of distribution are you looking at? We're also going to consider issues of data access. So do you have offline data access? You can fit your entire matrix in memory, or are you seeing this matrix evolve over time, sort of continuously adding new rows to it in a streaming model, or perhaps it's just so big that it lives on a hard disk, not in memory, and you have to stream over the rows in order to access the data. Okay. So our goals for imputation, they're going to be, can we get high accuracy imputations? Can we quantify the uncertainty of our imputations? Like, can we get confidence intervals for each imputed value? Can we estimate the impact of these imputations on downstream analyses? And can we understand correlations between the features or columns? Okay, so let me tell you about my new favorite model for this class of problems, which is the Gaussian Copula model. I'd love to take a quick poll and ask, like, how many people have seen Copula models before? Okay, mostly no. Yeah, head shaking and hand raising works. Cool. Okay, mostly no, some people yes. Okay, so here's the idea. Essentially, the Copula model, it's a system for separating the marginal distribution of each feature from the correlations between the features. Okay, so you can separately model each of these, can simplify your modeling a little bit. And the Gaussian Copula model is a special case where the correlations between the features look Gaussian. Okay, so here's the formal definition. So we're going to say that a random vector X follows the Gaussian Copula model with correlation matrix sigma and marginals F. If there is some latent vector Z, right, that's normal random vector mean 0 and correlation sigma. So correlation matrix, not covariance matrix, okay? The diagonal of sigma is 1. And X is generated by running that right, Gaussian random vector Z through a marginal map. Okay, so this marginal map, this is it's a collection of functions. Each of these functions is entry-wise monotonic and maps the corresponding entry of Z to the corresponding entry of X. Okay, I'm going to show you some pictures to make this make more sense. But basically, we've got this entry-wise mapping between elements of this Gaussian vector Z and elements of the X's that we saw. And basically what that mapping is doing is it's taking care of the marginal distribution of X. So you tell me X is binary, fine, right? My function fj, it's going to be a step function. You tell me that X takes on 7 values, fine. My f is going to be a step function, right, with 7 steps. And if you tell me that X has some crazy particular real distribution, I can find an F that maps a standard Gaussian to that crazy real value distribution. So why would you use a Copula model like this? I think the most important feature of this Copula model, so I mean, there are 2 aspects to it, right? On the one hand, there's this Gaussian part. Everything's really simple in the Gaussian part. You can do, right, you can prove beautiful theorems, you can estimate things really efficiently, you can get confidence bounds, no problem. But on the other hand, we've got this very strong data-driven aspect, which is the marginals. And those are very easy to fit to arbitrary distributions. And they'll nail the distribution. They will get the distribution right, or at least fit your data perfectly. A little bit different. So it separates. So it models nonlinear rulers. So let me tell you a story to illustrate what I mean by a nonlinear ruler. Imagine that you were trying to understand how loud various concerts were, and you measured 3 features of concerts. You measured the sound level in decibels. You measured the energy of, some displacement of some, membrane, right, by the sound waves. Notice that those are related to each other by a log transform. And you asked your friend Jim how loud he thought the concert was on a scale from 1 to 10. Okay. So in some sense, right, all of these are, they're directly correlated with each other. They're measuring the same thing, but they're on wildly different scales. Okay, one is an ordinal with values 1 through 10. One is on a log scale, and the other is on, the exponential of that thing. So you'd like to be able to get at the fact that these are perfectly correlated. They're just measured on different scales. So in the Gaussian Copula model, the correlation comes out perfectly. I mean, you would have the correlation matrix just be rank 1. And the marginals would do the work of mapping them to the appropriate measurement distributions. Okay. The third nice thing about these Gaussian Copula models, I guess it's worth mentioning the theoretical property, which is Sklar's theorem, that says that any multivariate joint distribution can be written in terms of univariate marginal distributions and a copula that describes the dependent structure. Okay, so the only thing that keeps this model from being completely general is the fact that I've said the dependent structure is Gaussian. And you might say that's it's a significant restriction. On the other hand, there are a shocking number of analyses that assume that the data itself is Gaussian. So this is certainly more general than that. Okay. So let me give you an example. So here's an example of a cutoff function f. Okay, so this is a function that maps, right, this latent vector z. So I'm showing one entry of the latent vector z. Each entry of the latent vector z happens to have a standard normal distribution, right? And you can see that from the fact that the vector z is distributed normal, 0, and sigma. Sigma is a correlation matrix, so the entries on the diagonal are 1. So that means the distribution of each entry of z, the marginal distribution of each entry of z is standard normal. Okay, but we've got this function f, and what that's doing is it's mapping the standard normal z value to a value of x that we might observe. So here, values between negative infinity and -1 are mapped to the value 1. Values between -1 and 1 are mapped to the value 2. And values 1 and higher are mapped to the value 3. Okay, so we've got some way of mapping between the Gaussian thing and an ordinal observation, an ordinal with 3 levels here. Okay, so worth remarking a couple of things. So when x has a continuous distribution, it takes on all possible values. Then the function f that maps x to z to x is invertible. But when x has a discrete distribution, as it does here, then this function is not going to be invertible, right? One value of x could have come from any z in a wide range. Okay, so we're going to write, still the inverse is going to play an important role in what comes next. So I'm going to write f inverse for this set valued mapping. So f inverse of x is going to map a given observation, say an ordinal value like 2, to the interval of z's it could have come from, in this example between -1 and 1. Okay. Any questions so far? Okay. Okay. So let's talk about the sort of the multivariate structure now. So here's an example for why looking at these Copula correlations is going to be really important. It's going to change your answer. So imagine that we had some data that was correlated. Okay. So and in fact this data is Gaussian. Okay. So I've got the marginal distribution of this variable I'm going to call Z1 is normal, and the marginal variable of that one, that's Z2, that's also normal. Okay, and they're jointly normal. Now I'm going to measure this using a particular nonlinear ruler, an ordinal ruler. So I'm going to truncate the values of Z2. So if you're above this first horizontal line, you're going to get value 3. If you're between these two lines, you'll get value 2. And if you're below the bottom line, you'll get value 1. Okay. So when I truncate, here's the resulting plot of the data. And I could truncate. And so now you'll notice that the sample correlation has changed dramatically. Sample correlation here used to be 0.8. Now it's down to 0.6. Okay, I can do the same thing along the this Z1 axis. So I'm going to truncate values to the left of this line to 1. In between here, I truncate them to 2, and above there, I truncate them to 3. Okay, when I do this, in fact, there are only 7 points represented on the plane. So actually, just looking at those points doesn't tell you very much. I should tell you how many of these, how many examples, right, land on each of those points. And so that's why I'm showing the marginal distribution, the marginal histogram along each axis. Okay, so you can see on x1, most take on value 2, a couple take on value 3. There's only one with value 1, and then similarly on the x2 axis. Now, if I look at the sample correlation here, I get 0.5. Okay, so if I just did a naive, I want to understand how related are these two features. If I just naively compute, right, the correlation between x2 and x1, I get a very different answer than if I had access to the real z's that are driving this, right, that are driving this phenomenon. Okay. So I'd love to figure out how to get access to the real z's, right? But the data that I have is these x's, these ordinal observations. Okay. So let's think about the multivariate structure of these distributions, because that's going to be the key to recovering the true z value. Okay. So imagine that. So my observations. So here I'm showing the z's on the left, the x's on the right, and the map between them, which is by these marginal functions f in the middle. Okay. What I'm going to show. So here I'm showing the PDF of each z. Right, and I told you the marginal PDF of HC is standard normal, though the joint distribution, right, there's some correlations between them. Okay, so the joint distribution is not, zero identity, Gaussian zero identity, it's Gaussian zero, some correlation matrix. Okay, on the other side, I'm showing you the marginal, the distributions, the PDFs of X. Okay, so you can see X1 has a continuous distribution, so does X2. X3 is ordinal with 3 levels, X4 is binary, and X5 is ordinal with 3 levels. Okay, and these are, I mean, these distributions are very easy to write down. Right, PDFs of converge very quickly. Okay. So let's imagine that in a given row of my data table, I've made the following observation. I know the value of X1. I don't know the value of X2. I know the value of X3, I know the value of X4, and I don't know the value of X5. So I've got 2 missing entries in this row. Okay. Now with X1, it's actually very easy to figure out how to map it backward and figure out the corresponding value of Z1. And the reason is that that I know this function f has to be monotonic. Okay. And so as a result, like for example, the 99th percentile of this distribution has to match the 99th percent, like let's say the first percentile of this distribution should match the first percentile, right, should map to the first percentile of this distribution. The median of this distribution needs to map to the median of this distribution. Okay, the 75th percentile of this distribution has to map to the 75th percentile of this distribution. Okay, so it's very easy to map back and forth between these real values. Okay, so I know exactly the value of Z1. For X2, no idea. So it could be anything. Z2 could be anything. X3, right? I know that it takes on value 2. And so once again, by matching quantiles of these distributions, I can say I know that Z3 has to be within this interval. For X4, I know it takes on value 1, not 0. So I know that Z4 has to lie in this half open interval. X5 I don't know anything about, so Z5 could be anywhere. Okay, that's as far as I can say about hard constraints on where the vector Z must lie. Okay, so you can see in terms of these hard constraints, Z has to lie in a product of intervals. Okay, the vector Z lies in a product of intervals. But I might know a little bit more, right? If I have a guess as the correlation between the elements of Z, maybe by looking at other rows in my data set, right? I might be able to get a sense for the correlation between the rows of, between the elements of Z. And as a result, I could say, well, now that I know that the value of Z1 is here, that makes me, you know, maybe I know that Z1 is correlated with Z2. Okay, so then I think actually Z2 is much more likely to be over here than it is to be over there. Okay, so I can narrow it down further. Okay, so that's the picture of how the math is going to work, and now I'm going to have to show you. the math. Okay. First, let me tell you sort of what work we're building on in this model. So, Peter Hoff had a beautiful paper in 2007 introducing the Gaussian copula for ordinal data, and he showed how to fit it with Markov chain Monte Carlo. You know, the nice thing about that is it's, you know, pretty general. The bad thing about that is it's very slow and has a lot of tuning parameters. So it's a little bit tricky to get it to work in practice, and it doesn't scale to large data sets. Han and Liu had showed how to fit a Gaussian copula for real valued data only. And they do that just by using like a Pearson's correlation statistic. So it's very nice, but not general. It doesn't work for mixed data. Ganti et al. Proposed a model. This was with Becca Willett and Laura Balzano, I think. They proposed a low-rank model that used nonlinear marginals. So the idea, actually, the motivation is very similar, saying, you know, maybe the data, you know, it has some underlying latent structure, and so there's some nonlinear transformation on top of it that maps you to the data that you see. But that model was not probabilistic, and they fit it with like alternating minimization. And there's a super weird thing that happens when you have a very flexible semiparametric model, you fit it with alternating minimization, is that you can end up overfitting dramatically, and every iteration, actually your predictions get worse. Very strange phenomena. That method doesn't work. I'm going to show you a method that does. You really need to take into account the probabilistic structure. Okay. Anderson, Bergman, Kinshir, Winoda, and Temi Kolda introduced another model motivated by the Copula model. Basically, they assume that the mean of the distribution is low rank, and then there's some diagonal covariance that. So somehow they were motivated by the Copula model, but it doesn't quite. Anyway, it doesn't quite have the structure, so it's both slow to fit and doesn't get as good accuracy. Okay, so our method, so we introduced an EM method that uses a similar model to the one that Hoff proposes, still the same Gaussian copula model. The nice things about it is that it handles real Boolean, ordinal, and missing data. We don't know how to do categoricals yet, so that's next up. It's fully probabilistic, which means you get confidence intervals for estimates. It has no hyperparameters. So to me, I think that's awesome because, you know, however long it takes to fit it, you're done once you fit the model once. And you can fit it with a fast approximate EM algorithm. Okay, so I'm going to show you how this works. Okay, so back to the Gaussian copula model. What do we have, right? We've got a latent vector Z that's normal 0 sigma. Sigma is the correlation. And X that is so Z maps to X via these entry-wise monotonic functions that I'm calling the marginals. Okay, so I've got two parameters to estimate. So let's imagine that first, though, that I've estimated these parameters. Okay, I know the marginals and I know the sigma. I want to show you how you can do imputation and uncertainty quantification once you have these. Okay. So once I have these parameters, the invertible marginals, let's say that I've got invertible marginals, just the easiest case, right? So that's where all the distributions are continuous. And I've got this correlation sigma. Now let's suppose that I see some entries in a new row, okay? I'll see the entries x obs, where obs is a subset of the columns. Okay, and the missing entries are the remainder of the columns. So So here's how I impute the missing entries using the normality of the latent vector z. Okay. So first I map the observed entries to latent entries, right? So some entries of this Gaussian vector. And now I use the fact that the missing entries of this latent Gaussian vector are normal conditional on the observed entries. Okay, so this is standard, marginalization of a Gaussian. Okay, pretty straightforward. So the mean, the mean looks like this. The variance looks like that. Okay, actually a sure complement appears in the variance. Okay, so how do I make predictions after I've seen this? Well, I might predict that the most likely value of z miss is just the expectation of z miss given z obs. So that's the mean of this Gaussian distribution. Okay, of course I could also compute confidence intervals this way too. Confidence intervals for every entry of z miss. And I can map those back to the observed space by just running the entries of z miss through this marginal function f. Okay, so it's actually like everything is very straightforward at this point once you have your model straight. Okay, right. So you can view it also in this space. Okay, and I've already explained this picture enough, I think, so I'm going to continue. Okay, what if one of the marginals is not invertible, right? So that means that one of the columns, one of the features in my matrix takes on either Boolean or ordinal values. Okay. Well, the idea is very similar. Okay. So the latent, again, right, the latent missing entries are normal given z obs. Okay. And I still might want to predict the missing entries with the mean of the conditional distribution of z miss, but it has to be conditional on x obs, right? Because z obs, I don't know it exactly, right? I know that z obs is in some product of intervals, but I don't know exactly what it is. Okay. So what I want is the expectation of z miss in terms of the obs, right? Conditional on x obs. And this simplifies quite nicely. Okay, so I just have something involving the correlation matrix times the expectation of this, right? The observed, the corresponding observed entries of this Gaussian vector given the observed entries of x. Okay. So now I want to map this back to the observed face again using the marginals. Okay, so everything kind of goes as before. And I can compute this expectation again using the correlation matrix. Okay. Why would you bother quantifying the imputation uncertainty? Well, you might want to understand the imputation equality. You might want to, for example, produce a confidence interval for every imputed entry, or even sort confidences among imputed entries. Okay, maybe you'd like to be able to say, this is the entry I have the most confidence in, this is the next one, this is the next one. That can be useful for maybe a recommender system, right? You might want to recommend, for example, movies that not only you think will be liked by the customer, but that you're very confident will be liked by the customer. Okay. And you might want to quantify the impact of imputation on downstream analyses. That's very useful for social science settings. So, you're a social scientist, you did some survey, there's some missing data, still you want to be able to report, you want to be able to do really standard analyses so that everyone will understand you and believe you and they won't question your methodology. But you'd like to know how the missing values are affecting the uncertainty. So that's quite important. Available methods, there's sort of two categories. One is based on single imputations. So these might be things like probabilistic PCA or noisy low rank matrix completion. And there are some methods based on multiple imputation. The way that these usually work is you resample from your data. So you take bootstrap samples of your data, you fit, a model to each bootstrap sample, and then you perform the imputations on each bootstrap sample. Okay, then that gives you a bootstrap sample of the imputed values for every entry, and you can, report that, report, for example, confidence intervals using that bootstrap sample of the values in each entry. But these tend to be, a little bit less restrictive. You can use a broader class of models, but they're quite slow. Okay. Okay. What you're able to get using R methods is okay. It feels a little bit like the best of both worlds because right, you're fitting a single model. You get an entire distribution of this Gaussian latent vector. You can map that forward to a confidence interval in the observed space. So I'm running a little bit slow, so I'm not going to read this to you, but this is exactly what you get, right? Okay. You can also quantify the uncertainty for ordinal observations, and that's a little bit funnier because you might not. It's not clear that a confidence interval is actually the right notion for ordinal observations. Instead, you might be more interested in the probability that your imputation is actually correct. And what's cool is you can bound the probability that your imputation is correct using the variance of the latent Gaussian z-value given the observed x value. In fact, you can even okay, you can even verify when you can be sure the imputed value is correct. So this is cool. Okay. Okay, so now let me tell you how you fit the parameters. Okay. How do you find the right correlation matrix sigma? How do you find the right marginals f? Okay. To estimate the marginals, I guess I've already told you about this, right? The way that you do it is you map you make sure that you write down the cumulative distribution functions for each of for z, which is always the CDF of a normal, and you write down the CDF of your observations in a given column of your matrix, right? Which you just look at the empirical distribution. That's easy too, and you just map quantiles to quantiles. Okay. So I can write that down in math. Here's what it looks like in math. But I think the picture is better. Okay. Okay, and I already showed you over here what that looks like, right? If the observed x is at the 10th percentile, right, of the distribution of x1, then the z1 should be at the 10th percentile of this standard normal distribution. Okay. Okay, so now let's talk about how we estimate the correlation matrix. Okay, so given an observed matrix X and invertible marginals. So we're warming up with the easiest case, which is that everything is observed and I've got invertible marginals, okay? In that case, as the most basic idea would be to estimate the copula using maximum likelihood estimation. So let's write down maximum likelihood estimation for this model, okay? So the first thing I would do is compute the latent Gaussian vectors given the observed vectors xi. And I write down the log likelihood, right? And this is just a Gaussian log likelihood. Okay, so it takes this form. And I guess it's worth, so you stare at this for a while and you see, look, right over here, right, is the empirical correlation, a covariance matrix of the z's, right, of these Gaussian vectors. Okay, and in fact, this likelihood is maximized by that empirical covariance matrix. Okay, now this is a little bit funny because we know that, right, sort of based on our model assumptions, right, we're looking for a correlation matrix, not a covariance matrix. So we can improve the estimate just a little bit by scaling this empirical estimate to a correlation matrix. It doesn't make a big difference, but it helps in practice and makes sure that everything is consistent. Okay. Okay, so that's the case where everything's observed and everything's continuous, which is the easiest case. Now, suppose you could try to do the same thing for data where you've got some missing entries. So in every row, you've got some observed entries and some missing, and you've got marginals that might be not invertible. Okay, so where f inverse is set valued. Okay, if you try to estimate the copula using maximum likelihood estimation there, you can write down, the likelihood of the data given the parameters, of the parameters given the data, and it looks like this. So you get a sum over each row, each data point, each say person in your voting sample, of the log of well, right, it would be the log of the Gaussian PDF, but you need to integrate over all the possible latent vectors z that correspond, right, that could correspond to your observations. Okay, and here's the problem: is that even computing that integral can be expensive. Okay, much less optimizing over it. Okay, the really nice properties that allowed us to just write down the solution in the fully observed case came from the fact that we could just match the log against the this sort of exponential Gaussian density to make things look linear, and we can't do that now. We have an integral in the way. Okay, so what do we do instead? So here's where we use expectation maximization to help handle this problem. Okay, so here's what the EM algorithm looks like. And in fact, it's maybe the algorithm that you would have written down. If you just thought about the problem, you might have just written down this algorithm. So it takes a very natural form here. Okay, so the input is the observed entries xob and the marginal f. I'm going to initialize. I guess actually all I need to initialize is my correlation matrix, and I'll initialize it as the identity. So the first thing I'm going to compute, right, is the expectation of the covariance matrix of the Gaussian ZIs. Okay. Right, and this is right. It's the natural thing to compute, right? In the case where I've got everything completely observed, right, the best estimate for my correlation matrix is a scaled version of the empirical covariance matrix. Okay, well here I don't have the empirical covariance matrix, but I can take the expectation of the empirical covariance matrix, conditional on the observations that I have, the marginals, and the important thing to note here is that the expectation of this empirical covariance matrix also depends on my current estimate of the correlation matrix. Okay, but my current estimate of the correlation matrix comes from, right? I had to guess it at first. Okay, but now once I have that empirical covariance matrix, I do the same thing that I did before. I scale it to a correlation matrix. Okay, and that's my new estimate of the correlation matrix. Now I repeat. Okay, until convergence, and I output the sigma hat. Okay, so we can say some properties of we can't state that this globally converges to the to the optimum. I wish I could say that, but EM theory. I have to say my PhD student Yuxuan introduced me to EM theory. I was advocating alternating minimization, and I can tell you with great certainty that alternating minimization does not work for this problem. That marginalizing over the latent values really matters here. Pretty interesting. But there's some nice things about this EM approach, very natural, but not nice things include that you can't show global convergence. But we can say that every step increases the likelihood. It produces a consistent estimate for the correlation matrix if the data is missing at random. Okay, so if the missingness only depends on observed entries, not on unobserved entries. And the third thing that's worth saying, and I'm not going to get into this unless people ask questions afterwards, is that the E step is actually quite challenging. Our approximate EM method. So this is not something that's easy to compute. You're computing the expectation of something with a Gaussian density, but over a truncated product of intervals. So our approximate method uses a fast approximation that just is based on sort of one-dimensional integrals. So we're only doing one truncated Gaussian integral at a time, a one-dimensional truncated Gaussian integral at a time. Okay, how well does it work? Okay, so first let me show you that it computes well and it computes quickly. So I'm comparing the approximate EM method to the Hoff's proposed MCMC method. Okay. So this is a synthetic data experiment with 2,000 rows, 15 columns. I take a random correlation matrix, and I'm going to say that the first 5 columns have exponential distribution, so they're real valued. The next 5 are binary, and the last 5 are ordinal with 5 levels. And the way I'm going to compare a lot of algorithms here is in terms of this, the scaled mean absolute error. The scaled mean absolute error says, how far off are my imputations in the L1 norm, divided by how good it would be just imputing with the median value from each column. Okay. And so that's a nice measure, because it means if you're doing better than median imputation, your scaled mean absolute error is less than 1, and otherwise it is greater than 1. Okay, so if your SMA is greater than 1, then you should stop using your fancy method and just impute with the median. So here's what that looks like. So our method is in red. That's the Copula EM method. Hoff's method that uses MCMC is in blue. Okay, and because we're using an approximate EM method, you can see that so we don't always converge down to the same value. Okay, so when it comes to the continuous data, so all of these are performing better than median imputation, at least after long enough times, right? Here Hoff's method is worse than median imputation, but after 50 seconds it becomes equal to median imputation and then improves. So for continuous data, Hoff's method seems to converge so slowly, it's not even clear that it's converging to the right thing. I believe it is converging to the right thing, but very, very slowly. Okay, whereas ours converges down to a low value quite quickly. For ordinal data, both methods converge nicely. Our method converges faster, substantially faster. About a factor of 5 faster on even the small data set. And for binary data, that's where things get a little bit interesting. Okay, so our approximation to this expectation works best when the intervals you're looking at are small. In the binary setting, all of the intervals that we're integrating over are half open. Okay, so they're as big as they can be. And as a result, Hoff's method that doesn't have this approximation is able to get down to slightly lower values of the error than our method. On the other hand, our method is substantially faster. Okay, so that's what we're getting at with the approximate EM. Okay. The estimate of the correlation also, we're converging so much faster that it's not even quite clear that Hoff's method is converging to the right thing. Okay, and here this is in synthetic data, so we know the true correlations. You can compare this to a bunch of other methods for missing value imputation on the synthetic data, and you can find the Copula EM has the best imputations, the lowest error, compared to a bunch of other methods, including parametric methods like semiparametric methods like XPCA, non-parametric methods like Miss Forest, which is based on random forest ideas, and impute FAMD, which is based on also on PCA. I guess it's also interesting to see that for high enough missing ratios, many of these methods do worse than median imputation. Okay, I can show you how this works on a couple of, a real data set, a couple of real data sets. So this is the General Social Survey. It's a survey that's administered to, it's been going on for many, many years. It's administered to a bunch of people, and they ask them a bunch of questions that are kind of interesting questions. So we decided to look at, in particular, at 5 questions. So we selected 18 questions total in this from this data set that had between 2 and 48 levels, so they were all ordinal. 25% of the data was missing, and we masked an additional 10% so we could evaluate the error of our imputations. So what we found is, again, compared to a wide variety of other methods, the Copula EM method is outperforming sometimes substantially in imputing these missing values, okay, and doing much better than median imputation. Okay, and these are things like, what is your social class? What is your quality of life? How healthy are you? How happy are you? How would you rate your income? Okay, so what's kind of fun about this, right, is you get the correlation matrix when you're done. And so you can look at the entries of the correlation matrix and say, okay, which of these variables is substantially correlated with each other. So here's a plot of where we're keeping as edges the large correlations between some interesting variables. So you can notice some interesting things from this, like, how happy you are depends on your, overall quality of life and your satisfaction with your finances. It does not directly depend on your income, right? So it's kind of important for PhD students and, the master's students, thinking about what their next career step should be. Okay, it only depends through your satisfaction with your finances. Interesting. Okay. So here's, I think I should probably, I think I'm going to show you this one last experiment and then wrap up pretty quickly from there so that you have time for a couple of questions. So this is an experiment on movie lens data. So this is the data that's like the standard Netflix prize problem. You've got a bunch of people who watched movies. You've got a bunch of movies they watched. Their rating on those movies, ratings between 1 and 5, and most of the entries are missing. Okay. So you'd like to figure out which movies they'd like to watch. So what we did is we restricted here to the 207 movies that have at least 1,000 ratings. So that's still a lot of movies. So we picked all the users who rate at least one of those 207 movies, which means that we have some users who only rated one movie. Okay, and this is sort of the classic example where people like using low rank matrix completion. On the other hand, the data is clearly ordinal. The ratings are 1, 2, 3, 4, 5. Okay, so actually it's very strange to use low rank matrix completion and impute non-integer values, possibly even negative values. Okay, in this data set. So it turns out if you use Copula EM, you get, again, lower mean absolute error and lower root mean squared error. And that's kind of surprising because a lot of these methods are using as their explicit target, right, minimize the sum of squared errors on the observations. Okay, whereas we're using this, probabilistic model. Nevertheless, right, and so it's kind of nice, right, rather than targeting a particular objective function, we're saying, no, we want the best model fit. And it enables us to do better on both mean absolute error and root mean squared error. Okay. One thing worth noting here is that the best rank selected using 5-fold cross-validation for different of these low rank methods can be quite different. Okay, so we found that the best rank was 99 for soft impute, it was 6 for XPCA, and it was 8 for generalized low rank models using the bigger versus smaller loss. Okay, so it makes you a little bit nervous about attributing the property of rank to this data set. Right? I'd say rank is, so maybe low rank is a useful tool for not overfitting here, but I don't think it's a fundamental property of the data. Okay, okay, so I'm not going to be able to say almost anything about this, but I guess I should just tell you that we've got a low rank version of this Copula model. The only change is that you say the covariance matrix is low rank plus diagonal instead of being general. And in this low rank model, you can fit it much more efficiently. So actually the number of flops per EM iteration scales with the number of observations in your data set, which is about as good as you can ask for. So that scales to extraordinarily large data sets and performs well. You can show that the confidence intervals what we compute are calibrated and are short, so they're nice confidence intervals. They work well, So sorry, I ran out of time for this. And we also have an online method, which makes the fitting even faster. It also allows you to handle problems where the data comes in sequentially over time, and even do a little bit of change point detection. So that was a recent paper that we have up on arXiv. Okay, so I think I'm not going to tell you anything about that. The other nice thing about that is that it allows you to adapt your model to a changing data distribution. Okay, so if the correlation matrix structure changes with time, you can figure that out and you can change right along with it. Okay, we've got 2 implementations, one in Python, one in R. We've got 3 papers out on this, one at KDD, one that's appearing at NeurIPS this year, and one that was in an ICML workshop, and a full paper, full version is on arXiv. So what's great about this? The Gaussian Copula model, my new favorite model for missing value imputation. It has no hyperparameters. It outperforms a lot of fancier non-parametric methods. It yields confidence intervals for imputations. And it's fast and easy to estimate for moderate numbers of columns, or if you assume a low rank covariance matrix, even for very large numbers of columns, like recommender system scale problems. Great. So with that, let me pause and see if there are any questions.
Great. So let's maybe we'll we'll consider that the talk wrapped up, the proper part. So let's thank our speaker. I guess a little virtual clap for a very interesting talk. So yeah, I would have my camera on, but somehow my webcam's been a little funky lately, and it's. But maybe we'll do a little. I'll kind of run a little. We'll call on people to ask questions. So if you have a question, if you could just use the raise hand feature, and I will kind of moderate that. So maybe we'll start with Shane Henderson. Please go ahead.
Yeah, thanks, Madeleine. It was very interesting ideas. I've thought a bit about copulas off and on over the years. So the first question that I have, and probably the one that I'll lead with because it makes sense, I'll wait for other people to ask. When you're doing imputation,
Yes.
so you're given a partial bit of information about your X, because you've got a few missing values. So the way that you're phrasing that is you map back into the Z space, and then you're living on a hyperrectangle, which could be semi-infinite. So the way that I was thinking that you were going to describe imputation was to somehow sample from that partial normal and then just map it forward through your marginals.
Yes.
So have you got an efficient way of doing that? Because that's actually not an easy problem, I think.
No. So essentially, it's right again. You've got the sort of computing the expectations, and that's where the approximation that we're using is quite important.
Right, but I don't think necessarily that. I mean, that's probably the right way if you want a single value. But if you wanted to get the distribution of what could be the missing values. I don't think there's a. I don't think there's a.
Yeah. So I guess we've been thinking about confidence intervals for single entries, rather than sort of confidence intervals for or getting the distribution of a given row. So we're not.
Right. So I think.
Yeah.
There are some natural.
So I think that's the big difference.
Yeah, I think there are techniques that one could use to sample from this the conditional distribution.
Yeah.
Conditional on what you know.
Right.
All of them would require at least a non-trivial amount of computational effort to do it.
Yes.
And I was interested if you were heading in that direction with your work, but it sounds like maybe not.
So we haven't so far. There are some applications where you do need to be able to where we would like a sense for the distribution of the entire vector, but I guess I don't have compelling enough applications that it feels worthwhile to put in the computational effort that it would take, as you point out.
Right, but even getting the conditional distribution of one of these variables,
yes,
it's a sort of a truncated normal.
Yes, that's right.
So you can do it computationally, and is that
right.
the way that you did it?
Yes. Yes.
Okay.
Yeah.
Thank you. So Dave, can I ask another?
Yeah, go ahead, please.
Okay, thanks. So when you did the fitting of sigma, you said, well, the unconstrained maximizer of MLE is just the covariance matrix, which may or may not have, in fact, probably won't have ones on the diagonal. So then you did this.
That's right.
That rescaling, does that correspond to if you were to solve a constrained maximization?
So this is actually very strange. So I don't think it. So I don't think it does. So we thought about ways of actually solving a constrained problem, and the computation gets a lot more gnarly for almost any way of representing it. Right, I kept wanting to imagine this rescaling as some kind of projection. In fact, we tried out other kinds of projections onto the set of correlation matrices, and they don't work as well. At least any of the ones that we tried out. I still I'm actually not sure about this question. Is the rescaling that we're using projection in some metric? And because if that were true, then you could show that you get improvement by basically Pythagorean theorem. But I'm actually not sure if it's projection in any metric. So
yeah, I agree, because
it's a simple question.
Yeah, but I agree, because the set of correlation matrices is it's a Stiefel manifold, and so you're somehow having to project onto that manifold.
Mm-hmm.
And there's
That's right.
doing that.
That's right. But there are lots of ways of getting there. And for example, just truncating the entries is a pretty bad idea here. On the other hand, from a practical perspective, it doesn't matter very much, because especially when you have a lot of data, the empirical covariance matrix will be very close to a correlation matrix anyway. So it's not a big difference.
Cool. And then thank you. And then maybe just one last question. So the Gaussian copula is a convenient one that has a lot of nice features,
Yes.
but it is just one copula.
Yes.
Have you thought about would there be motivations for considering others?
Yeah, I guess I don't have a strong taste among other copula models. The computation here is already challenging enough that we're having to do approximate EM. So once again, I would want to be strongly motivated by an application where the Gaussian copula really didn't work. The other reason why we're, to start with Gaussian copula is that so many of the models for missing value imputation are already based on Gaussians without any marginal transformation afterwards. So by basing your method on Gaussian copula, right, you can ensure that you improve on that state of the art. For example, probabilistic PCA is kind of widely used, which is a low rank Gaussian without the copula.
Yeah, I agree with your pragmatic perspective there. I think it's the right one.
Mm-hmm.
At the same time, I think sometimes you may be motivated by other forms of copula, just because of physical things you might understand.
Yes. So if you have any particular correlational structures in mind, I'd be very curious to hear.
Okay, thanks.
So maybe I will ask a question if I don't see any other hands at the moment. So is there kind of a proper notion of a conditional rank where you'd say, well, I have a mixed kind of data matrix. If I were to fix the Boolean ones and I knew the rest of it was low rank for any fixing of the Boolean ones, has that been formalized, and like what would that mean? I mean, I don't know what you'd have to think. It's not a square matrix maybe, or what's the, but it would seem like a natural, if the formal notion of rank doesn't really make sense when you have mixed data,
yeah,
that might be something one might ask.
Even in the case where your data is completely continuous, right? If you take a low rank matrix and you run it through a log entry wise, it's not low rank anymore. So
right. But I guess so for the application you're thinking, is the general, like for the applications you discussed.
Actually, what I said doesn't even make, what I said, it's true, but it actually doesn't even make sense, because a low rank matrix usually will have some negative entries. You can't run it through a log. I mean, there are serious problems with having your, there's some serious problems that come up with these models that say, I know what the map is. I'm not going to learn the map from data. I know what the map is from my low rank parameters onto the observations.
Okay, so but maybe let me re-ask the question a little, because this was something that had occurred to me during the talk at some point. Like, I know at the start of the talk you started by reviewing some of your previous work about in why is a matrix might a matrix be low rank, and the meaning of that. And then like it seems we switched to talking about copulas and left that concept behind, and it wasn't clear we ever came back to it. And
no.
So then, is there some hope of having an integrated view here, or is the message if you want to do recovery in some settings, you would use low rank,
No.
and
I
in
mean,
some
so
settings, you use something else.
Here's the way that I view that literature. So, I started out, highly motivated by the idea of low rank. It works well in a lot of data sets, and you can ask, right, is the low rank of these data sets fundamental, or is this just a mathematical artifact of something, right? Is it a good approximation, but it's not actually, the true phenomenon that's generating the data? I guess the perspective of the Udell and Townsend paper on why are so many data matrices approximately low rank is that it is just a mathematical artifact. It arises out of a very, very general class of generative models, but it's you can view it as some kind of Taylor series approximation to the truth. Okay, and once you have this idea that low rank, it's not fundamental, it's actually just an approximation. You just say, okay, well, what's it an approximation to? What regimes is it a good approximation in? Where is it a bad approximation? And where it's a bad approximation, what's a better model? Okay, and that's sort of precisely what you were seeing in the numerical experiments here, is that using, like in these, long skinny data regimes, or even like relatively wide regimes that I didn't show you with the low rank Gaussian copula, the low rank approximation just doesn't perform as well as a model that explicitly learns about the distribution of the data in each column, right? Which is what the Gaussian copula model does.
So I will ask one more quick thing and then go to Mike Todd, who I see has the hand up. And I guess the one final thing that I was a little confused by is, since you have it for Boolean, but then you said for categorical, it's unclear. I guess my first thought was, you could just reduce the categorical to Boolean. And maybe the question is, can you do better than some exponentially complicated thing, or what's the right?
With reducing categorical to Boolean, right? So you've got a one-hot encoding, so the normal way to handle one-hot encoding is you say, right? So there's some latent, right? So maybe there's some latent propensity for having each of those one-hot entries be on versus off. Right, and you might map, sample from a, multinomial logit, right, in order to figure out which of these entries is on, which of those entries is off.
Sure.
Right. Okay, but that's very different than this So in the Gaussian copula, all of the uncertainty is pushed into the Gaussian part, and the map from this Gaussian latent vector to the X vector is deterministic.
Right.
And that's really important for the fact that.
But maybe
the covariance matrix. Okay, so I don't know. I mean, there's not
but is categorical just saying it's a number between, say, 0 and 5, or maybe I misunderstand what categorical.
So categorical. What I mean by categorical is unordered categories. Nominal is another word for this. Rather than levels of education is ordinal. Favorite flavor of ice cream is categorical.
But I still remain, couldn't you could always map any finite number of categories to.
You can, but I think Madeleine's point is that the Z space is ordered, but your categorical space is.
I see, so you lose the monotonicity in that way. Okay, got it. That makes sense, thank you. Mm-hmm. Okay, then Mike Todd, please ask away.
To unmute. Okay, now I'm unmuted. Actually, my question is very related to this. I was interested in the ordinal case and your social science application. So it seems to me that a lot of the variability between the different rows is that one person's FI is not another person's FI. Where you put in the how satisfied, what your relative income is very different for different people, but you might get some information about that by how they rank their satisfaction with that financial situation. So have you considered a random model on the FIs as well? And ways of getting one imputation from another?
A small child has burst into my room.
Is it a 1 or a 2?
Okay. What's that?
Is the child a 1 or a 3 or?
2.5. Yeah, the kinds that can burst in.
That's not an ordinal one. Sorry.
That's right. Sorry, you're gonna have to. I'm gonna have to ask you to re-ask.
The FIs may differ between the people? Is it possible
yes,
to have
yes.
a
The
model
fitting,
on the
yes.
FIs?
Yes. So I think this is super interesting. Yes, it's saying that the people don't just differ in their latent Gaussian, but actually they have different marginals. There are lots of different, lots of different models you can write down for this. Essentially, the problem is that there's more degrees of, so if I say, every person, right, is represented by, this short vector z, especially if this latent Gaussian vector comes from a low rank plus diagonal correlation structure, then actually I can represent every person with a low dimensional vector. Okay, so that means there's not that much that I have to learn about each person, and I can learn that efficiently with not too many observations from that person. But if I say that every person has their own nonlinear function, I need many more degrees of freedom to represent that nonlinear function, right? It's easy to learn if I've got 1,000 people, 5,000 people, but if I have only one person and that person is only answering 10 questions, I really can't afford to learn a nonlinear function there. This is actually a huge problem. One application that I've looked at for there is paper reviews. So imagine in these large CS conferences, right, where every reviewer rates 6 papers. Every paper is rated by maybe 4 reviewers. You really, right, this is a very, very, very sparse observation model. You don't have enough information to learn anything nonlinear about either the reviewers or the papers. And yet, for sure, exactly what you're talking about should be operating, right? Some reviewers are more harsh, some reviewers are more lenient. So certainly there's a lot more information that you should be learning. A low rank model won't cut it, and yet you don't have enough data to learn that. So it's a super important question. I don't know a good way to address it.
Could you tackle like a multimodal copula?
Yes, that is, in fact, that is what Yushuan is working on right now. So the idea would be using this kind of model for clustering, right? So you imagine like a mixture of Gaussians type model, but mixture of Gaussian copula type model. Again, I think this same question that Mike Todd brought up is really relevant there, which is do you think that each of these, right? If you imagine that your data is a mixture of Gaussians, is it a mixture of Gaussian copulas, or is it a mixture of Gaussian copula? So is the marginal transformation at the end of the mixture of Gaussians, or does each element of the mixture have its own marginal transformation? If each element of the mixture has its own marginal transformation, actually I'm not even sure the model's identifiable.
I think it's hopeless then. But
yeah.
It's such an approximate structure for the joint distribution anyway. Maybe you pick the thing that makes the most sense mathematically.
Yeah. So you pick the one that you can do. Is sometimes the answer, and then you see how well it works.
Great. Are there any other questions, comments? Okay, if not, then let's thank our speaker again for a very interesting talk. Virtual applause once more, and I guess we'll wrap it up there. Then we'll proceed like that. Thanks a lot, everybody. Have a nice day. Thank you.
Thank you.
Thanks for all the questions.